So we took a last step in our abstraction process last time. We considered the open set properties in metric spaces. Then we took that as the defining relations, the defining conditions for a topological space. We have defined what a topological space is, which specifies a list of subsets of the given set as open sets, but with certain consistency properties. And those consistency properties were borrowed from the open set properties in metric spaces. Then we have noted the following, but let me remind you of that. We had this proposition. When we start with the metric space, and tau sub m, we let that stand for the set of all open subsets of X with respect to M. Well, then we have noted that tau sub m is a topology on X. We have gone through this last time. Now, Xm is a metric space. X tau sub m, that's a topological space, but we will make no distinction between these. We'll take them to be the same. Then we consider the following example. We started with any non-empty set. Now, since the first condition in the open set properties, thus in the definition of a topology, is that the topology contains the empty set and the entire space, well, any topology on cap X must contain these two sets, the empty set and cap X. So we asked whether when we restrict the list of open sets specified to these two, whether this would be topology. We have seen that it is. And we refer to this as the indiscrete topology. Now, the other extreme, that is, well, letting all subsets of cap X belonging to belong to the topology, that is 2 to the power x, that's the largest. Well, that turned out to be the topology as well, and that was the discrete topology. Now, we have noted with this, when M is the discrete metric, on X, well then tau m turned out to be equal to tau 2. Because here, with respect to the discrete metric, we have seen all subsets of cap X are open, but that's exactly what this topology says. So we gave the following definition. Let X tau be a topological space Well, can we find a metric M which actually induces the same topology as given in here? Well, we decided to refer to this topological space to be metrizable in that case. We say that x tau is metrizable if there is some metric M on X with the topology produced by this metric tau M is nothing but the topology we started with. And in which case, we refer to tau as the topology on X induced by M. Now, according to this is metrizable. Now, the question is, well, let's check whether this is metrizable as well. If I remember correctly, that's where we stopped. Did we check that whether this was metrizable or not? No. No, okay. But let us avoid the trivial case when X has just one member. Well, in that case, this will coincide with tau 2. Because if you have a singleton set, the collection of all subsets of that is just the empty set and itself. We know that that's metrizable. And there is only a unique metric on that, because the domain of the metric will be a singleton. Suppose X is the unique member of cap X, well then MXX, that will be 0, and that will be the unique metric. Now assume that X has, this is to denote the cardinality, the number of elements in cap X is larger than or equal to 2, and let tau 1 be the indiscrete topology on that. Now let's proceed as follows. Let us suppose that this is metrizable. Suppose there is some metric M on X with tau M being equal to tau 1. Now, the way we will utilize that this has at least two distinct members is, well, considering those two distinct members and apply M to that. What we know is what we know in that case is that MAB, that will be positive. Now, if this is A, this is B, and this is the distance, I can take half of this, that will be positive. I can form the epsilon ball about A, but then by definition of the radius in here, this will exclude B. It will include A, but exclude B. But what do we know about epsilon balls in a metric space? They're open. So we will have produced a set which is open, which is different than both the empty set, A is in here, and the entire space, B is not in here. So let's write that down. Set epsilon equal to 1/2 MAB. This will be positive. Now, the epsilon ball, with respect to M about A, we know, like any other epsilon ball, that belongs, that's open with respect to M. Another way of writing it is this. But A is in B M epsilon A, so that B M epsilon A is not the empty set. Moreover, MAB, that's just equal to 2 epsilon, and that's clearly not less than epsilon, implying that B is not in this epsilon ball. Thus, Bm epsilon A is not the entire space. So, tau m cannot be equal to tau 1, the contradiction, with the supposition that this metric m actually metrizes the given topological space. Okay? Now let's see a weird, non-standard example of a topological space. Okay? So far, what do we know? Well, each metric induces a topology. That gives a whole family of examples. But for that, we don't need the notion of a topology. The notion of a metric suffices. Then we took two extremes, and one of these, well, that turned out not to be metrizable. But let's take the following. Now let's take this subset of R as the space for our topological space. Now here, the definition of this is the set of all x in R such that 0 is less than or equal to x less than 1. So this set is defined entirely in terms of this order structure. Okay? Whether it's open, whether it's closed, what subsets are open, what subsets are closed, that depends upon the topology we impose on it. Okay? Well, the usual topology is one of those, but if we impose something else, then the notion of openness and closeness, that changes entirely. Now, define tau to be the collection of all sets of this form such that y is in the unit interval. Here, if this turns out to be topology, that's what we are about to check, then the open sets will be all these sets, the sets of this form. Okay? Now then, let's check. First, the empty set and the entire space, whether they belong to this collection. Now, firstly, 0 is in 0, 1. So I can take this as y. So this interval, that is the set of all real numbers which are larger than or equal to 0 and less than 0, that's in tau. But what's this set? Well, there is no such number, so this is the empty set. There is no x which is both larger than or equal to 0 and less than 0. 1 is in 0, 1 as well. So 0, 1, that's in tau. I take y equal to 1, but that's the whole space. So the first condition in the definition of topology, O1 is satisfied. Since it's simpler, let's first check O3, which says if A is in tau, B is in tau, then so also should be A intersection B. Let A, B be members of tau. Well, what does that mean? Cap A and cap B, they both belong to this collection. Now, there are, say, y1, y2 in 0, 1, such that A is of the form 0, y1, it's of this form, and B is of the form 0, y2. Now, if I take the intersection of these, I'll be taking the intersection of these two intervals, and that will be 0, y, where y is just the minimum of y1 and y2, but the minimum of y1 and y2, that will be in the unit interval as well, which simply means that A intersection B belongs to this collection. Thus, A intersection B, that is in tau, O3 is also satisfied. Now let's come to O2. Here we will take any non-empty collection from here. Well, in doing that, we use a non-empty set as an index set, and we take a collection labeled by members in that intersect, such that each of which belongs to here, and then we take the union of those. Now, let I be any non-empty set and assume that G alpha is in tau for any alpha in this index set. Now the question is whether the union of all these G alphas, that's a member of tau as well, to check that. Well, firstly, by definition of tau, for each alpha in I, G alpha is of this form for some Y alpha, that depends upon what G alpha is, belonging to this unit interval. There is some Y alpha in the unit interval such that G alpha is equal to 0 y alpha. The question now is, if I take the union of these g alphas, whether that will again be of the form 0 to y, 0 included, y excluded, for some y in the unit interval. But what's the natural candidate now for such a y? Well, the supremum of y alphas, if it exists. Now set S equal to the set of all y alphas, alpha in I. Well, in order to apply the supremum principle to this set, two things must be satisfied. This should be a non-empty subset of R, but since I is non-empty, this is a non-empty subset of R. Secondly, this should have an upper bound. What's an upper bound? Well, each y alpha is less than or equal to 1. Now, this is clearly a non-empty subset of R, and 1 is an upper bound of S. But then by the supremum principle, this has a supremum. Y equals sup S exists. By the supremum principle, y equals sup S exists. Now there are two things left. Is the union of g alphas equal to the interval from 0 to y, 0 included, y excluded? Secondly, whether this y actually is in the unit interval. Now let's start with the second. As 1 is an upper bound of S, well, this is the least upper bound, so y is less than or equal to 1. As pick any alpha in I, now y alpha, that's, well, let me write it in this order, is larger than or equal to 0. But this in particular is an upper bound of S, so this is less than y. Y is also larger than or equal to 0. So y is in 0, 1. Thus, when we show that the union of g alphas is equal to the interval from 0 to y, that will complete the proof. Now, I will go through that in verse, but leave showing that to you. Now, check that. The union of g alphas, alpha in I, is equal to 0y. Now, how shall we check that? Now, we will take any x in here, then x will belong to some g alpha. That is, x will be larger than or equal to 0 and less than y alpha. But y alpha is less than or equal to y, the supremum, so any point in here belongs to here. Now take anything in here, say x, but now x will be less than y. Y is the least upper bound. Well, if you take anything less than that, there must be some member of the set in between. There will be some y alpha for some alpha, which is larger than or equal to x and less than y. But that means that it will belong to some g alpha. So we have shown in words at least, writing that, do that, that's educative, so that's why I'm leaving it to you. You show that this set is a subset of this, and this is a subset of this, getting this equality. So, this is, in tau, O2, is also satisfied. Thus, tau is a topology on X. Let's consider also the question, any questions about this? Let's now check whether this is metrizable or not. What's your conjecture? Well, it's best to think pictorially first. Pictures are useful, but they should not be over-trusted. So that's our motto. This is 0. This is 1. So this is our set. Suppose it's metrizable. That is, there is some metric on this set which induces this topology tau. But let's go back. Let's remember the way we thought in showing that the indiscrete topology in the presence of at least two distinct members in the space, well, that was not metrizable. We took two different points. We separated them. We formed an epsilon ball about one, which excluded the other. Okay, so well, that's what a metric is about. Now here, 0 is a member of the space. Well, 1/2 is another one. If you take any metric m on here, m of 0, 1/2, that will be positive. If I take half of that and form an epsilon ball, where epsilon is half the distance between 0 and 1/2, according to the metric m, this will include 1/2, but that will exclude 0. Well, this epsilon ball, that will be an open set in the metric space, because any epsilon ball is open in a metric space. But can that be a set which excludes 0? Can that be a member of the topology? Can it be open with respect to tau? No. Each open set here contains 0. So let me quickly write this. While I write, let's go over that once more. Suppose there is some metric m with tau m equal to tau. Now, we took 0 and 1/2. Well, in fact, instead of 1/2, any point different than 0 belonging to the space would do, okay? They are in X with 0 different than 1/2. So, m of 0, 1/2, that will be positive. We take half of that. Well, anything larger than 0, less than this, that would do as well. Set epsilon equal to 1/2 m 0, 1/2, that will be positive. Now, the epsilon ball with respect to m about 1/2. Well, about 0, if I take the epsilon ball about 0, which excludes 1/2, that will not do the job, because that will be open with respect to the topology as well. This is in tau m, but 0 is not in there, because we have chosen epsilon in such a way that the distance from 0 to 1/2, according to the metric n, is twice epsilon, 2 times epsilon, which is larger than epsilon and not less than epsilon. Implying that well, this is a subset of cap x which does not include 0, so it cannot belong to tau. A contradiction. Because we have tau m in tau, but we have, that was our supposition, but we have produced some set in here which does not belong to here. So x tau here is not metrizable. Now, at least these two examples, this example plus the example of the indiscrete topology on a set with at least 2 members, well, they show that a topological space is genuinely more general than a metric space. There exist topological spaces which cannot be expressed in terms of a metric, via a metric. Next, let's again consider another example. This time we'll start with 2 different metrics on one and the same space and compare the topologies, these 2 different metrics. They will be quite different than each other in use. Now, again, this is another example. Now let's consider the set of all natural numbers or the set of all positive integers. Let one of the 2 metrics we will consider be the discrete metric. Let M1 be the discrete metric. On x, that is mxy, that's equal to 1 if x is different than y, and 0 if x is equal to y for any xy in n, which is x. Do we know what topology this induces on n? Yes, it's the entire power set. We know that tau m1 is equal to the entire power set, the set of all subsets of n. Okay? Now let us take as the second metric the usual distance between any 2 natural numbers. Define M2 on n cross n into R by M2xy. What's the usual distance between these? It's just the absolute value of x minus y. for any xy in N. Is this a metric on N? Yes. Well, we know that this is a metric on R, but when you restrict that to any non-empty subset, that will again be a metric. But you can easily check this is a metric. Now, M2 is a metric on N. Now the question is, what is the topology on the set of natural numbers induced by M2? Well, let's check the following. Let x be in N any natural number and epsilon equal to 1/2. We know that the epsilon wall about x with respect to the metric M2 is open with respect to M2. Let's check what that is. Now, B epsilon, which is 1/2, x is a natural number. Here we have M2. This is the set of all natural numbers y, whose distance from x is less than 1/2 according to the usual metric. But what's this set then? It consists of x only. Because no matter what other natural number, what other integer you take, the difference is larger than or equal to 1. So this is just equal to x, but is open with respect to M2. That is singleton x, that is a member of the topology induced by M2 for any x in N. Now we know phi is in tau M2, and for any non-empty subset A of N, can we decide that A is open? Well, A is equal to the union of all singletons such that x is in A. But each singleton is open, thus this union is open. This also belongs to tau M2. That is tau M2, that's equal to the power set of the set of all subsets of N as well. Now here we have two different metrics, M1, this, and M2, this, but they both induce the same topology. If, regarding the topological structure of a space, it is only the open sets what matters, that is, well, the collection of all open sets. Well, if that's the same, then the topological structures are the same. Then although these, they're different than each other as functions, quite different than each other as functions, but they induce the same topological structure, we will refer to such metrics as being equivalent to each other. They are not equal, they're different objects as functions, but as they lead to the same structure on which we focus, Well, they're equivalent from that viewpoint. So let me define that. So we'll start with any non-empty set. And we take two metrics, M1 and M2, two metrics on X. We say that M1 and M2 are equivalent if the topology M1 induces is the same as the topology M2 induces. Thus, the usual distance and the discrete metric, they are equivalent on the set of natural numbers. Now, before proceeding any further, the first question in today's homework that is concerned with this. Now, formally, it might look complicated, but it's not at all. Well, let me go over the question in here, the first question, in pictures. There you have two sets, A, B, which are disjoint. Okay? Now you're given a metric M1 on A metric M2 on B. So these are separate structures. But we wish to construct a metric on A union B using M1 and M2 as the main building blocks. Now, if I take 2 points in here, there are 3 possibilities. Both might belong to cap A. Well, then I use M1 to measure the distance between them. They might both belong to B. Then I use M2. But if one is in here and the other is in here, that is what we should decide about, how we shall decide what the distance according to the metric to be constructed will be. Now, we do it like this. We take a point A, an arbitrary point A, but fix it in here, and we take a point B and fix it in here. The metric on A union B that we will construct, that will depend upon what points we take. If I have X in here, Y in here, I take the distance of X to A, I take the distance from Y to B, but there is no distance defined between A and B. And I declare that to be 1. They're distinct, so, well, this one could be any fixed positive number, real number. So, for the metric to be defined on A union B, in this case, MXY is defined as M1XA plus M2BY plus 1. So that's just that metric. It looks formally as if it were not simple, but that's the main idea. The question now is, I can take here another metric, M1 prime, which is equivalent to this. Another metric here, M2 prime, which is equivalent to this. Now, let me refer to the first metric in terms of M1 and M2 as rho. Let me take A and B to be the same. Just define the new metric by replacing M1 by M1 prime and M2 by M2 prime. I'll get a rho prime metric on A union B. The question is whether rho and rho prime will be equivalent to each other. If I use equivalent metrics on cap A and on cap B respectively, these taken arbitrary but fixed points, they're the same. So that's the question. So I guess this makes it much easier to understand what that question is all about. But now, let's turn back what our aim in introducing a topological structure was. Now, we wanted to formalize, given a point and given a set, when is that point arbitrarily close to the given set, to give a precise meaning to that. Now, we were very close to that. We almost had done the job in metric spaces using epsilon balls. But now we have extended that to the notion of a topological space where the notion of distance disappeared. So we actually, by taking one more step towards a more abstract construct, we have made our job, well, instead of simplifying or making easier, we made it more difficult. But the notion of an epsilon ball, that was the main building block in metric spaces, in formalizing the arbitrary closeness of a point to a set as well. Now, what should the counterpart? We should find the counterpart of an epsilon ball in a general topological space, and we should do that using open sets, because that's the only thing we have. Now, what we'll do is we will now introduce the notion of a neighborhood of a point. And that will be done as follows. Let X tau be a topological space. X a point there, and U a subset of X. We say that U is a neighborhood of X with respect to tau if there is some open set G such that it contains G and that's contained in U. Here we have only open sets. So X, well, that should really be in the interior of U. Pictorially, that's what this means. U could be large, small, and so on. We can take this as small as we wish or as large, but it's a subset which contains X. But that does not suffice for U to be neighborhood of X. Well, there should be some open set G which contains X and is entirely contained in U. Now, we'll look at what this notion means closer next time, and in fact, we will define several different relationships between a set and a point using this notion of neighborhood, and that will do the required formalization that we have been aiming so far but I guess we can stop it.